So one of the things that we said here is that we had the ideal op-amp model. And all we know is that the op-amp is a very complicated device. And because it's complicated, what we have to do here is that we have to simplify our picture. So what we want to do here is that when we simplify our picture here, our whole job here is essentially to really streamline our calculations. And this is what we find, okay? What we find here is that when I apply this ideal model, which is what? A mathematical model. And what we're doing here is that at the input terminals, 1 and 2, the currents going into the terminals are 0. The node voltages have to be the same. And when you start to look at what we're talking about, you're going to see that we're really not ever looking at, well, we do look at the difference, but a lot of the times you'll see that the difference is really, one of them will be 0. Okay, so we started off with, we're going to look at some circuit examples here. We start off with the voltage follower. And so what I'm going to do here is just to give you an idea of what these ideal conditions are. I'm going to go and I'm going to apply them to the voltage follower. So for starters here, I'm going to look at this node right here. So if I look at this node, that node is V1. And when you look at, oops, sorry, not V1, V2. And then when you look at this other node, you could see that there's a wire connecting that node to this node. And so what that means here is that this node right here is defined as V1. And then this other node over here is defined as V out node. So the fact that there's a wire connecting V1 to V out, it immediately tells you that those two have to have the same voltage. So when I look at this condition here, you're seeing here that there's a current here. I1 is equal to 0. But as soon as you look at that current there as I equal to 1, 0, the op-amp condition then immediately tells us that the voltage VR is immediately 0. Because that's what the calculational model tells us here. So from this condition, what it's really telling us here is it's telling us what? Well, if VR is equal to 0, then that means that V2 must be the same as VS. So if I come in here and I look at this thing, this immediately tells us that V2 must be the same as the source voltage. So that's what the current conditions for the ideal model tell us. So then the ideal model tells us that V1 and V2 must be the same. So then, okay, so if V2 is the same as V1, but we already said here that V1, because of the wire, is connected to V out. So right away, what this tells us here is that V out is actually equal to the source voltage. So in this case, if I look at V out over Vs, it has a gain of 1. In other words, this thing is going to behave linearly, assuming that I put out only, the positive voltages here. It's going to look like this. And of course, this will continue to go linear until it hits the saturation voltage. And assuming that the saturation voltage is at 15 volts, then that's where it saturates. Okay, let's go to the next one. This is the non-inverting amplifier. And remember, the whole idea of these two examples are really to get you to start thinking about, what does the ideal model say? So what I'm going to do here is that I'm going to solve this circuit 2 ways. The first way is going to be using node, and the second way is actually simple circuits. And I'll tell you one thing, simple circuits is a far better calculational way of doing things. Furthermore, you get to really learn what it is, but I think we should do both. So the very first thing you got to know is that when you look at the positive, the non-inverting node of the op amp, you always want it at the bottom. So in other words, this guy right here should be right here. So this is sort of like our little calculational routine. Now, you don't have to do that. It's just something that it's very systematic for me, and so then I continue to do that. This resistor right here is known as the feedback resistor. And so what I'm going to do here is that I'm going to go in and I'm going to draw in my nodes for the circuit for node. So what I'm going to do here is actually I'm going to make a copy of this because I'm going to want this a little bit later, and I'm going to just stick it down here for a minute. And then we can reuse this circuit here. So here I go. So the first thing that I want to do here is that I want to draw in all my nodes. So what I'm going to use here is I'm going to solve this. So I'm going to use the method of node analysis. So mesh cannot be used on op amps. Note that the plus and minus 15 volt sources that supply the op amp are not shown. Right? They're not shown, but they're assumed to be there. So what you're finding here is that you are missing the current input from these sources. The incoming current from these sources. Therefore, you don't have enough information to use mesh. You need all of the currents in the circuit to be able to analyze this. Therefore, one cannot use mesh. We can use node because we're calculating voltage differences, and that's a local thing. So here we go. So what I'm going to do here is that I'm going to do the counting. Okay. So in this case here, what we're going to do here is that let's do the counting. So what I'm going to do here is I'm going to put my circuit in here. Okay. Here's my circuit. And what you're going to see here is that I have my ground node. So I think it's worth putting them in here today. Right, that's my ground. And note, we know what this node is right here because we know that this guy here has a voltage of Vs right there. So how many unknown nodes do we know? And the answer is we don't know this node. And remember, what this tells us here, that this node is V2, so it's common to call this node V1. Now, you might be saying, but there's this other node right here, right? You might be saying that this is a node. This is not a node. What you want to do here is that you want to remember what a voltage-controlled voltage source is. And one of the things that we said here is that when I look at this, and we call that V out, and we say this is A times V in, question, is V out a node? Of course it's not. That's the value of the source. So it is not a node, but the value of the source. You know, I'm going to just delete this, and I can come back and get it later. It's a value of the source. So if you write an output node equation for V out, you're barking up the wrong tree. It has nothing to do that. So what we do here is that when node is applied to an op amp, never, ever write a node equation for V out. It's not a node. So what we're doing here is that we're using node analysis to write node equations for everything else. So what you're seeing here, in this case, when I say let's do the counting, there is only one node, and that's V1. So let's write the node equation for V1 then. So when you look at that, so then I have node V1. So when you're looking at this thing here, you can see that I have two resistors. So I'm going to come in here and I'm going to go R1, RF times V1. Then I have mutual. I have R1 with the ground. I have RF without. And in this case, no current sources. So what you're seeing here is that note what node equation does here. Look at this. I don't know V1. I don't know V2. What this does here is that this sets up two unknowns and one equation. So it's impossible to solve. So the way you get the second equation is you apply the ideal op-amp model. So the second equation comes from the ideal model, or maybe the ideal op-amp model. So now the op-amp model comes in here, and we know that I1, I2 is equal to 0. And what does that tell us? Does this tell us anything new? Well, let's go look at the circuit here. So if you look, this is the current of I2, but there's no resistors there, so it doesn't change anything. And then there's this current here. I1, that's 0. But no, there's no resistors along this branch. So what this tells us here is that there's nothing is gained here. So then I go to the next one. The next one says V1 must be the same as V2. But wait a minute, we already agreed that V2 is the same as Vs. So all of a sudden, the ideal condition then tells us that we know what the value of V1 is. So now we have two equations and two unknowns. So what I'm going to do here is that I'm going to substitute Vs for V1 in the node equation. So now I'm going to sub into node equation. So if you do that, you could see that I'm going to get R1, RF times V1, but V1 we know is V source, and this is 1 over RF, and this is V out. So now if I solve for this thing, you're going to see that V out looks like this. And that's what the amplifier does. A non-inverting amplifier does that. So that's the way the thinking of node analysis. So you apply node analysis. Only after you apply node analysis do you then come back and use the ideal conditions. If you use the ideal conditions first, man, you're going to run into trouble. So,
Carlos?
yes.
So I certainly have examples where, like class examples, where we've used node analysis and counted the output, the V out of the source as a node.
No, it can't be a node.
I mean,
it
these
cannot
are...
be a node because so if you look at this source right here, would you call V out a node?
Is this like a supernode thing?
No, no. You would call that a node. You would call that a node, but you would not call V out a node.
The two
Right?
greens.
This is a node. This is a node.
Okay, right. I agree with that.
And that's what I'm saying. So you cannot write a node equation for the value of the source. So another situation that I could say here. Let's call that V out 12 volts. Can I write a node equation for 12? No. But if I was writing node equations, that might be part of a supernode, or it may be connected to the ground. Those two green dots are nodes, but not the 12 volt. That's the value of the source. The value of V output is the value of the voltage controlled voltage source for the op amp.
So you're saying that upper node value, the above your dependent source, is not equal to V out.
Right. Okay. So the other method that I want to look at is I want to look at the method of simple circuits. And what you're going to find here is that this is just like not discussed in textbooks at all. And that really is too bad. And the reason why it's too bad is that what ends up happening is that you really miss a lot of the sort of like behavior of the circuit. And what we do when we apply this thing, I'm actually going to slide this over a little bit so that I can write some. I'll move it back here in a minute. Is that the idea here is that we, by applying the ideal conditions, immediately and start following the current flow in the circuit, one gains an incredible amount of op amp intuition. And I'm always into intuition. So what I want to do here is that I want to immediately apply the op amp conditions. And then just analyze and what's going on. So the whole goal here is to literally follow the current. Okay, so here we go. So immediately, what do I know? Well, I know, I want to get the right colors just to that, okay, red and green, okay. So the first thing that I'm going to do here is I'm going to look at just this red node piece right here. And then I'm only going to look at this green piece right there. So just by inspection, from what we've already talked about, we know that the source voltage is the same as the green. Now, the only time we really got to pay attention to the current on this bottom one is there's resistors. There's no resistors. So this guy, I2 equal to 0, doesn't tell us anything. Now, I'm looking at V1, and if I look at V1, what does this really tell me here? Well, I know that the current here, I1 equals to 0. So that means when I look at current flow in the circuit, where is the current flowing? Well, I know this is ground. I immediately can come up here and go like, oh yeah, this node right here. That node is V1, and of course V1 is Vs. So when you're looking at this thing, look how the current is flowing in the circuit. For starters here, look, here's the ground, right? We know this is the ground right here. So if that's the ground, and I have a positive voltage value or node voltage at V1, then of course the current must be going in that direction right there. But wait a minute, there's no current going down that red branch. So that means the current has to be flowing like this. So the current in this branch, which I'm going to call IX, is the same current in that branch. So now I play the game of Ohm's law. So a big part of this technique is using Ohm's law. Okay, it's using Ohm's law. So what I'm going to do here is that I'm going to focus on R1. So I know both nodes across R1. So if I focus on R1, what you're seeing here is that I know the voltages, right? I have a resistor. I could see that I have my ground node right here. I could see that I have my V1 node. So I know that this guy's V1, which is the same as Vs. And I know, of course, that that guy's ground. And I know that this guy's R1. So clearly, when I look at Ix, what I'm seeing here is that Ohm's law tells us what? That V1 minus 0 must be R1 Ix. So I know what that current Ix is, right? So this tells us here that Ix, of course, must be V source over R1. But follow the current. To RF. And what you're seeing at RF here, right? So this is what the first resistor tells us. The second resistor tells us this. So now I have RF, but now let's look at RF a little bit more careful here. I know one of the nodes, right? One of the nodes here is this node, and that node we already know is Vs. And there's the other node. Let's make this the blue node right here. And we know that that's the output node. So when I come over to resistor RF, you could see that this node is V out. But wait a minute. We know the current. That current is Ix because we know the conditions of I1 equal to 0, that there's no current in there. So it's going straight right by that node here. So therefore, what we're going to do here is that, here we go, Ohm's law again. And what does Ohm's law says? Well, that must be the high, that must be the low. So therefore, V out minus Vs must be Rf times Ix. So let's solve for V out. So if I solve for V out, you could see that this is Vs plus Rf Ix. But wait a minute, we know what Ix is. So then this becomes 1 plus Rf R1 times Vs, which is V out, which gives us exactly the same result using node analysis. A person who learns to see this way, oh baby, it's like chapter 2 all over again. You either see series and parallel or you don't see series and parallel. People who see op amps will like almost instantly using this technique go in and go like, oh yeah, I see it. And then you just start writing simple Ohm's law equations and you solve it. Okay, let's go to our first example. So I'm just going to keep applying this now. That's all I care about. Here we go. Example 1. So we'll use 2 methods, but at some point you'll probably see me just stop using node analysis. But I think it's important that we do both. Because, I mean, dude, this is an elegant weapon for op amps, the simple circuits. Okay, so here we go. Let's go look at this thing. So the thing that I want to do here is I want to do the following thing. So we want to use 2 methods again, right? We're going to use so we are going to use 2 methods, right? One is going to be node. The other technique is going to be simple circuits. So let's go look at that. So the first one that we want to use here is that we want to use the node. So the method of node. So here we go. So let's go up here and let's set this up. So the first thing that we want to do here is that when you're looking at the method of node, what you want to do here is that you want to go in and identify your nodes. And it's a good idea to do what? Start with the counting. So right away, we're going to go into here. We're going to look at this guy right here. And we're going to say, let's do the counting. So of course, we got our ground. So we don't count the ground. And we can immediately see here that we have one node that we know for certain. That node, of course, is 3 volts. So what are the unknown nodes? So remember, we don't count the output node. So what nodes do we know? Well, I mean, what nodes do we have to solve for? There's this node. And you could see that that node right there is V1. And then there's this other node, which is this green node. We're going to call this guy V2. And then there's this other node here, which I will not touch. Remember, no node equation for this node. This is just the output node. And so this guy's V out. So what you're seeing here is that I have what? 1, 2, 3 nodes. I have 3 nodes minus 1 source, so I should have 2 node equations. Which node does it have to be? It has to be node V1, node V2, and then I'm going to have, and now I'm going to have the ideal condition. So I should have 3 equations, 3 unknowns. So let's go write that. Let's go write the 2 node equations. So here we go. So the first thing I'm going to do is I'm going to start with node V1. So if I look at node V1, I have 2 resistors. So I'm going to have 10 plus 20 times V1. Any mutuals? I have a mutual with the ground, so that's 0, and I have a mutual with output. So then I'm going to get 20 V out, and that's 0. And you can see that is not a solvable equation. And then I have node V2. So if I look at V2, you could see here that I have 2 resistors in connection. So I'm going to have 10 plus 20 V2. There's no node 1. And then I have a mutual, one with the ground, which is 20, and one with 3. So then I'm going to get minus 110 times 3, and that's got to be 0. So right away, you could see here is that in theory, if you're going to use node analysis, you have to write down node first. And you could see that my unknowns are what? Out, V1, V2. And now let's go see what the third equation is. It's the ideal condition. So what do I know about the ideal conditions? Well, for starters here, note that the ideal conditions tells us something about what? It tells us I1. Now, where is I1? And are there any resistors connected to I1? Well, for starters here, this guy is I1 right here. And note there's no resistors. Look at I2. This current right here is I2. But there's no resistors right there. So what I2 tells us is that the current only flows in this little loop right there. None ever goes into the op-amp. And if you look at I1, what that really tells us here is that the current here and here must be the same. because there's no current going down into that red branch right there. So the ideal condition, so when I write down the ideal conditions here, so I1, I2 equal to 0, it tells us nothing. So what about V1 and V2? Well, when you look at V1 and V2, that means that the node voltage at V2 and V1 must be the same. So that means this equation then tells us that this is really V1 minus V2 equals to 0. It sets up a condition for that. So if I was to write a matrix for this thing here, right? So now I have a matrix solution. I have V1, V2, V out. And then of course I have my constants. So then if I start to write them out, I could come in here and I've just used the same things that I've done in the past. I'll come in here and I go V1, V1. So then I'm going to come in here and I'm going to write 10, 20, 0. And if I go up a little bit, this will then give me 1. So now if I go look at 2, there's 2 here, there's 2 there. And if I keep going, this is going to be 0. This will give me 10, 20, and finally minus 1. And then V out here, you're going to get minus 20. And that's it. So then I should have 0, 0. And all the constants are 0. So therefore, if I now plug this into a matrix,
That
We have a
second
constant,
constant
actually.
isn't 0.
that second constant is what? It's
3
not
tenths.
0. Thank you. You're right. It's 3 tenths. Thanks for the help. So if I go in and I actually get that calculation, what am I going to get here? I'm going to find that V out is then going to be plus 6 volts.
Carlos, this is at the very least inconsistent use of language. You're calling V out not a node, but you're using it in a node equation and then solving for it.
No,
As a
I
node.
agree. What I said was that you can
So what you're saying is like it can't be the leading, like V1 there is the way you're using the language is you're saying I wrote this node equation for V1, as in it is the node that to which the the 1/10 and the 1/20, those are the resistor.
So if I was to come up here,
to
let me show you what I mean by that. Let me grab this and bring it down here. So if I was to paste this thing here, now I can write node equations for, let's say this is V1 and that's V2. I can write node equations for V1 and V2. I can't write it for V out.
And so what I'm struggling with here is what's the difference between V1 and V out? Like I forgot what the value was that you got for V out, but let's say it was 5 volts or whatever. Where is that demonstrated in this? Okay, it's 6 volts. So where is that demonstrated in this circuit where you have the?
So when I'm looking,
well, you got to be CVS here, and I just want to see like the simplest circuit you can think of that would be around it, and tell me that the output is not 6 volts.
Yeah. So how about if we go to the other one, and then I
Sure.
think that one, well, that's the problem with node, right? The problem with node doesn't give you jack shit to think about intuitively, right? It's a piece of shit.
Uh-huh.
I mean, how many times have you heard me slam node and mesh? The fact is,
Yeah,
though,
it's
if
simple
you,
circuits.
oh, you mean you really want to understand what's going on? Whoa, maybe we should try the other technique. Let's talk the other technique and then let's go. I just look at node as really a calculational thing, right? It's oh, not that. It's sort of like you come in and you just sort of like, right? It's a non-thinker's, paradise with node. Okay, here we go. Baby, now let's use the elegant tool. That's what we want. So what do we know about this elegant tool? So what I'm going to do here is that immediately I go, are there any resistors here? No. So the current doesn't tell me anything. Are there any resistors on this branch? No. So what this immediately tells us here, so when we're applying the ideal op-amp model, what this tells us here is that I1 and I2, when you're looking at this guy, look for resistors on these branches. And what they do here is that they kill them off. So the fact that there's no resistors along these branches, right? This is not going to tell us anything new. So then I got to start following. So here I go. Let's follow the nodes here. So check this out. So note, if I know that this is 3 volts right here, and the thing that you want to see here is that I'm focusing now on V2 here. So look at what's special about V2. There's current coming from the power supply, the 3 volt source. So it's going this way, it's going this way. No current's going into that branch, so it's coming down. So in other words, this is really a voltage divider rule. So what I'm going to do here, so looking at node V2, what that tells me here is that it isolates the loop, which then means I can use VDR to get V2, which is the same as voltage as the 20K. So let's go do it. So here I go. VDR then says that the voltage across the 20K is going to be 20K plus 10, 20 times 3 volts. And when you compute that, okay, 3 over 30, 10, 10, 2, that's 2 volts, right? So I have 2 volts. But wait a minute, that's the same as V2. So I now know what that voltage V2 is, but that immediately tells us what V1 is. So then the ideal conditions here, or the ideal model, immediately tells us that V2 and V1 is now both 2 volts. So let's go. So now I'm looking at this thing, and what does this tell me here? I have a node now. This red node now is going to be 2 volts. And look at where the 10K is at. It's at the ground. So that means the current here is the current going through the 10K, but look at that. That red branch of node 1 tells us that this current must be the same here. So in other words, let's be careful. The current of the 10K here is also the current of the 10K there. So here I go. So now I just apply a series of Ohm's law. So now I'm going to apply Ohm's law, and Ohm's law says that if I want the current across the 10K, it's got to be 2 minus 0 divided by 10K. So therefore, it should give me 0.2 milliamps. So now I know what that current is, right? I know what that current is. So now I keep following the current. So I see the current through the 10K. So now I follow the current to the 20K. So now I'm going to follow the current to the 20K. And that's what I mean. You know, it kind of reminds me of Fruit Loops, right? Follow your nose, follow the current. So what you see here, that was pretty corny. Okay, I guess I'm showing my age here. So you could see when you come over here, look at this node. That node is V out. So now I can go find what V out is here. So again, follow the current here. Look what I'm going to use. Isn't that surprising? Ohm's law, right? I'm going to use Ohm's law again. So Ohm's law tells me what? It tells me follow the current. So if I'm at the 20K, you could see that the high of the 20K is V out. The low is the 2 volts. So therefore, I know that V out minus 2 must be the current of the 20K, but that's the same as the 10K. So we know that's 0. Ooh, I should be careful here. I made a mistake. It's the 20K times the current of the 20K, which is also equal to the 10K, which is the same as 0.2 milliamps. So that tells me then V out is then going to be 2 plus 20 times 0.2. So that's really 4. So I get 2 plus 4, which gives me 6 volts for V out. So you could see I don't run into that dilemma of whether to count V out as a node. I'm just solving this, using standard techniques where I'm just using Ohm's law primarily. Let's go to the next one. The next one's a gorgeous problem. Oh yeah. As far as op amps are concerned, this is one hell of a sexy problem, because this is just plain beautiful when you start to use this thing for, I don't know what is going on, for, sort of like actually seeing what is going on. So what we want to do is, again, we want to use 2 methods here. And so as I'm using these 2 methods, the first thing that I'm going to do here is that this time I'm going to start off with simple circuits right away. Okay, simple circuits. And so one of the things here is that this looks pretty gnarly. As it stands, this is really gnarly. So let's go look at the method of simple circuits. So when I look at this thing, probably there's the easiest way to think about this thing is to really focus on this piece right here. we want to come in and we want to look at this guy right in here. And what's really important here is that we just got finished with Thevenin circuit. And one of the things that we know about a Thevenin circuit is it has a voltage and it has a resistor in series. Now that's a really powerful statement, because what you find here is that if we replace the, the diamond subcircuit as a Thevenin equivalent, what does the circuit look like? Well, for starters here, we know that we have to have what? We have to have an R Thevenin. We know that we have to have this, but then if I start to draw the circuit, and then it's going to look like this here. And then you'll see that I have a resistor here. And this guy's a 30K. And then this circuit here, that's connected to ground. And this is a 10K. So I'm looking at this thing. And what we're really trying to solve here is that we want to solve for what? Well, for starters here, we want this node right here. Right? That node is V out. And now I want the current coming like this, which is I out. Now, what's really special about this circuit here? Well, for starters here, we can see here that this node right here, the positive input here, this is node V1, no, V2. But wait a minute, it's connected to ground, so that's 0. So this immediately tells me that this red node right here, which is what we call V1, that must also be 0. But look what's special about that V1 node. That means that the current through this whole branch right here must be what? Must be 0. So the first thing by recognizing this is that it does what? It kills off Thevenin's, it kills off the Thevenin resistor. So the ideal conditions kill off the Thevenin resistor. So in order to really solve this thing, you could see here is that this node up here, I think I'm going to change this node to a different color here. This node is really about what? This node is V Thevenin. So if I can, right, because it's connected to the ground, so if I can figure out V Thevenin, then the rest of the circuit is fairly straightforward, right? It's fairly straightforward. So let's go calculate that. So the thing that I want to do here is that the goal here is to now determine VTH. Okay, so our goal now is to determine VTH, because we know how to solve that problem, right? This is a fairly simple op-amp problem, because you could see here, if I could get that voltage, then I could get the current through the 30K. I mean, I got to look at the other nodes here, Really, it's really the current of the 30 and the 10 that really contribute to V out. So what I want to do then is that let's go look at this resistor here. I mean this voltage here. So let's do that. So what I'm going to do here is that I'm going to come in and I want to isolate this guy. So let's redraw this thing. So I know that I have two resistors that look like this. And then I have a source in the middle. And then I have two more resistors, of course, that do this. So if I look at the values of these resistors, they're crisscrossed, if I could say that. This is 10K, this is 10K, this is 30K, this is 30K. And what do we know? Well, we know that this guy is the ground, but I1 is 0 here. And if I look at this node up here, this node up here is V7 in here. So when I'm looking at this, I got to also remember that along this branch right there, I1 is equal to 0. So what you're seeing here is that there's no currents in the system. Now we can redraw this if we want, but I think I'm going to choose not to. So what you want to think about here is that this is my 6-volt source. And because I have two resistors in parallel with the 6-volt source, that means that the current has no choice but to follow this loop right here. And then here, the polarity must be like that. So all I have to do now is I have to follow a path to ground. We could follow any path you want, but here we go. So the path that I'm going to follow here is it's going to go along here. I'm going to go along this path, this way, all the way down to ground. So let's do that. So if I do that, what do I see here? So using the right branch, what does that tell us here? Well, I know that the difference between these guys have to be what? It has to be VTH minus 0, right? Because there's the ground right here. So I have the 30K and I have the 10K. Look at the polarity of these guys. So this guy's going to be what? So if I look at the path here, I come down, I'm going to hit what? I'm going to hit positive 30. So I'm going to get positive V30K. And then as I come down, you see I'm getting negative 10K. Right? So that's what the Thevenin voltage is here. So now all I got to do here is that I'm going to use voltage divider rule to kind of figure that out. Right? So from here, I'm going to use VDR to get the voltages of the 30K and the 10K. So here we go. So VTH minus 0, which I'm ignoring. So what's the voltage across the 30K? Well, using VDR should be 30K, 10K, 30K times 6 volts minus that of 10, which will be 10K, 30K into 10K times 6 volts. And after the dust all settles, I find that this guy is 3 volts for VTH. So now I know what the Thevenin voltage is. So now what am I going to do? I'm going to come right back to the circuit right here. I now know what it is. So if I know what that is here, so now we can determine V out and I out. So if I stick this guy back into here, what am I seeing here? Well, I don't care about the left side. All I know is that this guy now is 3 volts. Okay? It's 3 volts. You know what? Did I choose the right direction of current for this problem? Yep, it's going in. Good. So here I go. So note that there are 2 currents. There's the current of the 10, and then there's the current of the 30K. We're only interested in the one of the 30K here. So check it out. Ohm's law. Ohm's law tells me what? That the current, let me make sure I get that right. Oh, no. I can't calculate the current of the out yet. So look at the key right here. So that means the current is flowing between the 10 and the 30 have the same current. So check this out. So if I look at this current here, look at that current. This current is going in this direction. That's got to be the current of the 10K. So the current of the 10K is then going to be, right? It's going to be the Thevenin voltage minus the ground has to be 10K times I of the 10K. So what this implies then is that the current of the 10K then, of course, is then going to be 3 minus 10 milliamps. So it's got to be 0.33 milliamps, right? So this guy's going to be, but wait a minute. Since no current flows into node V1, that implies that the current of the 10K must be the same as the current of the 30K, but look at the directions of the arrows. There has to be a minus sign right there. So I now know what the current of the 30K is, which is what? It's the same as the current of the output, which is in 0.33 milliamps. So now I apply Ohm's law. So to get V out, then I'm applying Ohm's law again, which then tells us here that V out, well, really the current's going the opposite direction. So in this case, because of the way it's shown here, it's got to be V Thevenin, V out is going to be 30K times I out. But in this case here, you know what? I should have, let me do this here a little bit. Can I rewrite this just a tiny bit? Because I'm going to take this minus sign out. And I'm going to put that minus sign in here because this is one of the things that we're supposed to compute. So I know that that's the current right there. And so if that's the current here, then this tells me then that V out must then be V Thevenin minus this 30K times 0.33 milliamp. And if you compute this, this is going to be then 3 plus 9. So this gives me 12 volts for V out. So I now know the output voltage and I now know the output current. Let's go look at this in terms of node analysis now. So again, I'm just really following the current using this technique. Now, let's bring the hammer out. So what we want to do is that I want to go get that circuit again, and let's go identify nodes. So as before here, we don't write a node equation for the output voltage. Let me see if I get my color schemes good. Okay. So we know that this node here is ground. And we know that this node here should also be ground, but that's not how we write it as a node equation. Okay, because as a node equation, I have to, the only thing I know is that V2 is 0. Fine, because it's connected to the ground. But guess what? This is an unknown node. Okay, and then what you're seeing here is that there's a supernode here. Why is there a supernode? Because this is a voltage source not connected to the ground. So in other words, I know that I have a supernode right in here. So what am I going to do? I'm going to call this, how do I call this? I'm going to call this, if that's 1, how about if I call this node 2, node 3, and then I have a node all the way up here. There's this node. This node, what am I going to call? Well, if that's 1, 2, 3, I'm going to call that guy 4. And then, of course, I have my output node right here. So now, here I go. Note that, of course, the 10 volt is just the 10K on the right here is connected to the ground. So let's go do the counting. So if you see here, okay. So what you're seeing here is that I have V1, V2, V3, V4. So I have 4 nodes, right? 4 nodes. And I have -1 source. So I should have 3 node equations. So what do I have? Well, I have a supernode between 2 and 3. So therefore I have a super condition. And then I have node 1 and I have node 4. And because I have 4 unknown variables, I have to use the ideal condition to answer that question here. So I got 1, 2, 3, 4, 5. So I have 5 equations and therefore 5 unknowns. And what are my unknowns? It's got to be V1, V2, V3, V4, V out. And I can write a solver equation to include V out, which I probably should do that actually. So I'm going to take this out right here and I want to put a solver in here. So then I want a solver for I out. So therefore I got 6 equations, 6 unknowns. So then I got 1, 2, 3, 4. V out, I out. Right? So let's go do it. So let's go write them out. So if I'm going to write them out, what am I writing here? So for starters here, I'll start with, I'm going to start with node 1. I should have started with node 1 right away. Okay? Because when you look at node 1, what you're finding here is that that node is fairly light because there's no sources here, but let's go do that here. So here I go. So I'm going to start with node 1. So node 1, you see that there are 2 resistors connected. So I'm going to get what? I'm going to have 30, 10, V1. Then I have 2 mutuals, which will be 30, V2 minus 10, V3. And there's no current sources. There's no V4. So here's 0 right there. Let's go look at the supernode now. So I'm going to look at the supernode 2 and 3 here. And so here I go. So if I focus on node 2, I have 2 resistors. So I'm going to get I got V2. And then I see there's one connected to V1 and there's one connected to V4. So I'm going to get minus 10 V4 and there's nothing connected to V3. Okay. So that's, you know what? I shouldn't have done that. I should have just done this. So now I have my node V1 or V2, excuse me. And then because it's a supernode, I got to do V3. So V3 then tells me that I have to have 10, 30, V3, and I have 2 mutuals, which would be 10 V1 and 30 V4. And this is node 3, and this is node 2, and no current sources, so that's 0. Then I have my super condition. And my super condition says that 2 is higher than 3. So then I'm going to write V2, V3 equals 6. So now I need n equal to 4. N equal to 4 here, you're seeing that there are what? Well, there's a lot of them, right? There's 10, 20, 10, 30, 30, and 10. So let's go write that out. So if you do that, man, let's see. So I have 1, 2, 3, 4 connected to 4. So let's go write that. So then here's node 4. So I have 10, 30, 10, 30, V4. Now let's go look at the mutuals. So there's the 10 with 2, the 30 with 3. So then I'm going to write 10 with 2, 30 with 3. And then I have V out connected to 30, and then 10's connected to ground. So we don't consider that, so that's got to be minus 130 V out, and that's got to be 0. Okay, so I got node 4. So what else do I need? I need the ideal condition. Well, you could see that V1 has to be the same as V2. So then I have the ideal condition. So that says V1 minus V2 equals to 0. And then now we need a solver here. Well, you could see that the solver tells us that it has to be V4 minus V out has to be 30 times I out. So if I put in a solver, then this should be V Thevenin minus V out. Oh, I didn't call it Thevenin, I called it V4. And that has to be 30 times I out. So if I erase this, so now I have this, well, this matrix. I don't really want to write this out. How about if we say the following thing here, that I'm going to leave it as an exercise for the student, if I could say it this way. So we're really practicing the setup. So, you know, putting this into matrix form, solution, we get that V out is 12 volts and I out is negative 0.33 milliamp. So you get the exact same result. So the question I have for you, if you're a node person, I agree there's some comfort in not having to think. But this just seems to be a pain in the ass, but you know exactly what to do. But if you think your way through this, this is really nice. It's a powerful technique. So what we find here is that we're on to the next example, which I will not have time to finish. And now what you're going to see here is that this example is slightly different, but not that much different. It's the same kind of thinking here. And if you're doing the same kind of thinking, I mean, you can actually, you know, another trick that we can do here is that, you know, what's amazing about this thing, if you look at this circuit, if you use sort of like the simple circuits in thinking here, check this out. Look at this node right here. Oops, what am I doing? Check this guy out right here. If you look, that's ground. Wait a minute. That's ground. Wait a minute. That's ground. So if you're looking at this thing here, note that this node right here, right? If I come in here and I look at this node, note that these two 6K resistors have a green node and have a black node, the exact same black node. So guess what? Those two 6Ks are in parallel. So in other words, I can replace that with a 3K, with the 3K resistor. Isn't that wild? Okay, I'll have to stop right here. So thanks for showing up. I will see you guys on Wednesday. Hey, good luck on the quiz and good luck on the exam on Wednesday. Hopefully the stuff that I'm giving you is helping you. Okay, I'll talk to you guys later, okay? Hey, wait a minute. I'm gonna send out an announcement, but I'm gonna have to cancel out because I'm not allowed to pick up anything from the shipping until Thursday. And that's assuming it's even there. But there's rumor that the oscilloscopes are there. So during spring break, I'd like to see if I could hand out all this stuff out. Okay? So spring break, I really want to hand out everything. And you still have to keep your power supplies because you're still going to need them for a little bit. Okay, I'll talk to you guys later, huh?
See you, Carlos.
Okay, bye-bye.